Hey guys, how are you? I'm Manish here and I'm back with some physics here. Alright, we have a problem here. It's from Irodov, which is once again a great book. So let's read it. Plank of mass m1 with a bar of mass m2 on top of it lies on a smooth plane, alright. A force going with time t is F equals at is applied. Find how the acceleration of the plank and the bar depend on time if the coefficient of friction between the bar and the plank is equal to k. Alright, let's just analyze it. And I have just drawn some pictures for you just so you can visualize it more better, and it'll also help me. Okay, so first of all, what I'm going to do is I'm going to draw something called the free body diagram. Now this might sound very taunting, but it's just a separate figure of a body. You just mention on the forces that act on the body, nothing else. What is it doing? Is it moving or not? You don't care, just the forces. Okay, so here it is. So this is the M2, right? This is the bar on top. So there's a horizontal force acting on that body, and of course there is its own weight, which will always act in the downward direction. And there is one more force which acts like so. That is due to the normal reaction from the plank. So let's call that N for normal. And there's obviously as they mentioned, there's friction, so you can imagine that the friction is going to act in the backward direction because it's intuitive. It'll slow down, right? So that's the reason why it is. And let's draw the same thing for the plank at the bottom. Now there are a couple of more forces on this. There's of course its own weight, M1G. There is what else? There is a normal reaction from the ground, right? There's normal reaction from above due to the, I just call this N prime because just to differentiate between the two normal reactions we have here, and the normal reaction due to the bar on the plank. And there's one more force acting on this, that is the friction. And now we can use the Newton's third law, which says that all forces, internal forces, act in action-reaction pairs. So if it acts towards the left on the bar, then it must act towards the right for the plank, and it must be of the same magnitude, right? Okay, so we have drawn it. Now I want to tell you that the frictional force, its magnitude is, actually let me write something here, it is proportional to the normal reaction between the two planks, right? So you can imagine, the harder you press the two bodies against each other, the more friction they'll create, right? So it's kind of directly proportional. And that's too dark, and that you can remove the proportionality and you can write some constant times the normal reaction, and this constant is nothing but the coefficient of friction, right? Okay, so that is given to us. So let's now apply Newton's second law, if I believe is right. Now I claim that these two, the normal reaction on the top and mg on the bottom, will cancel. That's because this body right here, it's not moving up or down, right? It's just moving horizontally, so the net force in the vertical direction should be 0. So that's what it is. N equals m2g, but they're in opposite direction, so they cancel, kind of like. Okay, so I'm just going to write the horizontal force equations. So the body is moving towards the right, we know that. So the net force towards the right will be capital F minus small f, which is the friction. That is the net force, and now that will be equal to, according to Newton's second law, the mass of that object, which is m2 times I'll just write it as a2 because the accelerations will be different, as you'll see. Alright, so that is for the bar. Now we'll write it for our good old plank here. So what about that? And by similar arguments, I claim that these three vertical forces will cancel, right? Because you know that the plank is not moving up or down, it's just moving left or right, right? So the only force in the horizontal direction is the friction. So that is the net force on that plank, and that should be, according to Newton's second law again, m1 times a1. Beautiful. And now, as I said, small f equals k times n, where k is the coefficient of friction. Now let's substitute that. So you get f minus k times. Now I could write normal reaction, I could write n, but as I discussed with you earlier, n is equal to m2g because it's not going anywhere, right? So let's just write m2g in place of that n right there. So that's m2g, that is equal to m2 times a2. Okie dokie. And now by similar arguments I can say that, and these two have the same magnitudes, right, these frictions. So this will be k times the same thing, right, m2g, because they have the same magnitude and those things. Okay, that is equal to m1 times a1. And now all we got to do is solve for a1 and a2. Whoops, I opened up the wrong thing. So we'll just do that, right? Okay. So let's just rub it here. I don't want this because we have it on the right. That's a beautiful background there. Really, I've never drawn such a beautiful one. Okay. So we just need to solve for these. Okay. And now also I want to tell you that f is at, right, as they gave us. So I'll just simplify it here. From here I can write this as at minus k m2g equals m2 times a2. Okay. Now the bottom one, the top one, the blue one, is quite easy, actually very easy. You just have to divide the whole equation by m1 and we are done. So let's do it. From here, whoops, from here I can say that a1 is equal to, and a1 is the acceleration of this thing right here. Okay. Now a1 is k times m2g over m1. Okay, that is interesting. And now that is our a1, right? Now I can solve for a2, right? What is the question asking? Find how they depend on time. Okay. Okie dokie. Now let's solve the second equation here. Okay. So let's just divide by m2. So we get a2 equals a over m times t, and this m2 minus k times this m2's cancel. You get this, and that's it. We are done. Okay, let's see you. Thanks, YouTube.